Okay, first we want to say a few words about the motivation for doing things that we do in this course. Now, why should we put ourselves through the torture of solving all these equations? What's the point of it? So, motivation for linear algebra many engineering systems that you want to study and calculate something eventually boil down to a linear system. So what was a linear system? Linear system simply refers to a bunch of equations. For example, we took a look at some simple cases last time. You could have something like a linear system that people use in practice. There could be hundreds of variables here and hundreds of equations. It could be thousands of them or millions of them, really. And because of the size that we come across, we need to study this systematically to be able to be confident about the answers that we are giving. Now, where do such things come from? Let's take a look at one particular case. Suppose somebody wants to go to a hospital and do some non-invasive diagnostics, like want to do a CAT scan or something, just to check to see what is inside. So let's suppose here's a person. We take a square person, say maybe SpongeBob or somebody else. We want to see what is inside of his body. Now, we cannot just walk into his ear the way Pat does or something like that. We have to find some other way of figuring out what is inside of this creature. So the standard thing is to imagine, just imagine that we have cut this person up to several pieces. So we impose a grid on this person. Now, inside of each of these grid elements, there is some kind of a tissue. It could be bone, it could be muscle, it could be blood, or whatever else. So this tissue material is occupied, these cells are occupied with different kind of things. Since you are outside, you of course don't see what is there. You want to figure out what is there by some ingenious method. What do? One style is to send a wave. So you send the wave inside the body, the wave goes inside and comes outside. It has become a lot weaker. Why did it become weaker? Well, because it has been absorbed by this tissue. But different kind of tissue absorb the wave differently. The amount of reduction in the strength of this wave depends on what is in front of this. So the ratio of the strength of this to that one tells you some of all of these variables that have been blocking this wave. So you take one picture, that picture tells you about some of a bunch of variables, like one of these equations. The ratio of these two tells you the right hand side, some of the resistance of all of these tissues construct the left hand side. That gives you one equation. Well, one equation wouldn't do, so what do? There is some gizmo around here that rotates the density in each of these. The density in each of these blocks is going to be like one of these variables. The amount of reduction in the wave depends on the density that is present in that location. So you take a second look. That second look, the second picture, looks at different cells. Looking at these different cells at a different angle, it gives you a different equation. And then you go and do this thing and again, as many times as your resolution allows. Each time you are sending some wave from one side and you have a receiver on the other side that catches the wave, and everything is sent to the processor, a computer that solves this system of equation and tells you the density, and from the density you tell what is in a particular location inside the person's body. So that's a simple case that justifies why we are interested in linear algebra. Now sometimes you might be able to see something, but you want to understand it better than just visually looking at it. You are not looking at it as like a surgeon who wants to know what is where, but you want to know what is the underlying mechanism that makes some system behave in a certain way. For example, you might have a drum. Okay, a drum. When you hit this drum, the surface of drum starts to vibrate. Okay, goes up, goes down. Of course, not by as much as I'm drawing it. I'm exaggerating it. But something that oscillates has perhaps a membrane. That membrane is changing its position, causing oscillation. The oscillation goes into the air and comes to your ear, and so on and so forth. Suppose you want to study the relationship between the shape that is created here and the place that you have been hitting this object, or various other mechanism you might be interested in. What do we do in that case? In that case, again, we take this drum, we do a similar thing that we did here. It's called discretization. Discretization means taking a continuous object and breaking it up into a bunch of cells. These are imaginary cells just for our convenience. Now, each of these cells has a relationship with its neighbors. For example, if I consider this one, this cell is connected to its neighbors. Now, however you want to define the neighbors, we consider, say, these 4 items as the neighbors. The membrane is elastic, so there is each of these cells, in a sense, is like a spring that's either pushing or pulling the neighbors. So there is a connection between each of the cells and the neighbors. When we write down the physical laws, you might remember from your physics courses things like Hooke's law or other kind of laws that tell you how the push and pull is going to affect the location of an object. You end up with an equation. Each equation relates each cell to its neighbors. Once you write it, once you get across the physics of it and write the equation, you get one of these. You go to another cell, you write the relationship in that cell, that gives you another one of these equations. So you get a huge bunch of equations. If you solve it, you can predict the behavior of that membrane, and then you can go about your design problems or whatever else you have in mind. So linear systems are very common in engineering. Very basic thing many of you are going to be handling perhaps this semester, perhaps next semester, is that you are going to deal with circuits. Simple circuits have a bunch of resistance in them. Has anybody taken that course already? Okay, so these wiggly lines I'm drawing here represent resistance, like a light bulb or something. You can have a circuit, an electrical circuit that has many of these things in it, and much more complicated items, perhaps capacitors or inductors and so on. You want to know if you attach electricity to this object, to this circuit, how much current is going to flow through each of these electrical lines. Or this could be streets of a city, that you are just studying traffic in the city to see how many cars are going to come and go in each of these streets. Well, you have these nodes, and these nodes, some electricity is coming in and some electricity going out. Is that right? Let's suppose, for the sake of example, some electricity coming in and splitting in these directions and it's going. What does that tell you? That is giving you an equation. the amount of flow that is incoming has to be equal to amount of flow that is outgoing. It's like saying the number of cars that are coming into the intersection have to be equal to the number of cars that are leaving the intersection. Each statement of that sort is going to give you an equation. And then you have Ohm's law and other laws. You write them as equations like this. When you want to try to solve it, then you have to live with linear algebra. The bigger your circuit is, the bigger your system is going to be. And for very big systems, we need a systematic study of the topic to see what to do, how to employ algorithms, how to be sure of what we are doing, the efficiency of algorithms, and so on. So lots of topics come in. So that makes the motivation for the course. Now, let's go ahead and actually take a look at some cases. We are going to start from small cases and hopefully build up towards something sensible. Okay. Our main tool that we are going to use in this course is something that you have seen back in junior high. It's called the elimination method. Now, of course, that has been done for thousands of years, but since the systematic study of it was done by Gauss, this is referred to as a Gaussian elimination method. So Gaussian elimination, in his honor, this is referred to. Okay. Elimination means we try to get rid of some of the variables in the equation in the hope of simplifying it and solving it. If you have an equation that has been properly prepared and eliminated to a certain extent, you come across something that is called a triangular equation. Triangular equations, or equations with triangular form, are especially easy to solve. Let me just write down one of these things, example from the text. 2x plus 3y minus 2z is equal to, say, 7 or minus 7. 3y plus 2z is equal to 3, and 5z is equal to 15. This is called triangular form for obvious reason. It looks like a triangle on the left-hand side. This side of it looks like a triangle. Of course, when we write our equations, we put the variables underneath each other. All the x's occupy the first column, then the y's, then the z's. If after a certain reformatting your equation looks like this, we refer to it as triangular. So in triangular equations, there is no x in the second equation, there is no x and no y in the third equation, and if it was bigger, more and more of these variables have disappeared from our equations. Well, what is so great about this? The great thing about it is that the problem is almost solved. It's like just one step short of being totally completed. So how do we approach this? If we were lucky enough that our equation looked like that, what would we do? Yeah, we try to do it from the bottom and come back up. For that reason, it's, the method that we are going to apply is referred to as backsubstitution. Backsubstitution simply means if your equation has been reduced to this form, you start from the last one, you divide right-hand side by the coefficient of the left-hand side, you get your z. You take this z, put it back here, so by now you have 3y plus 2 times 3 is equal to 3. So you clean that up. This is 6. Subtract 6 from both sides. You get 3y is equal to minus 3. You divide by 3, and what do you get? Y is equal to negative 1. And then you step backwards. So by now, this is 2x plus 3 times negative 1 minus 2. And z, we got it to be 3. It's equal to minus 7. So 2x minus 3 minus 6 is equal to minus 7. That tells me 2x, this is minus 9, Going to the right hand side, we add a 9 to both sides. This makes it 2, I guess. And we get for our x, what do we get? X is 1. So here we summarize the solution. We got x equal to 1, y is equal to minus 1, z is equal to 3. So that is the solution. And there is no other. First of all, we can verify, we can check this thing by plugging it back to make sure we haven't done any incorrect arithmetic, anything. So one thing you want to do is to check that this is right. And second thing, notice the procedure tells you that there isn't anything else. We had no other options anywhere. We haven't skipped anything. Z has to be 3, and then y has to be minus 1, and x has to be 1, and so on. Okay. So that is in case we were lucky, and of course most often we are not lucky. The equations are not handed to us in a triangular form. That would be somebody else having already done the hard part, and we are just harvesting the result of his labor. What do the equations look like? The equations typically have a scattered form. There may or may not be all of these things here, but typically on the left hand side we have a filled set of coefficients and everything else like that. Now let's go ahead and take a look at a more typical example. So a typical example, (2x minus 3y minus z is equal to 4), and then here we have 7x plus y. No z is here, but we keep the shape. Minus 3x minus 2y plus 9z is equal to 0. Okay, this is more like a kind of thing we are going to encounter. Now, I'm sure you all know some way for solving this equation. You can all struggle and work on it and eventually get some number out. The issue is to be consistent and to develop a kind of an algorithm that you can delegate to a machine to do. So idea is not so much that to solve this one, you have done that 3-4 years ago. The idea is to develop the idea to a higher level and then work it out from that angle. So first we need some mechanism for helping us with writing and a notation and so on. So we develop a notation that comes along with these type of problems. We notice that if we insist on keeping x and y and z's in their own column, then we don't really need to write them anymore. Okay? If you know on the very first column these are all x's and these are all y's and these are all z's, then why bother writing them? So that gives us the matrix notation. So sometimes this course is being, instead of being called linear algebra, is called matrix algebra, because matrices play a major role in this course. What's a matrix that is associated with this? We have some stuff on the left, some stuff on the right. Depending on which one of these things you want to write, or perhaps you want to write all of them, you are going to have different terminology. If I take, again, we emphasize x and y and z are in their own column, then we just pick the numbers and, excuse me, don't pay attention to the variables. So second row I have 7, 1, and 0, and the third row I have -3, -2, 9. Numbers on the left, these are called coefficients. These are these numbers. So when we collect them in this array, we are going to call this the coefficient matrix. Right hand side is not given a name in the book, but we might just call it right hand side. So we have typically a bunch of numbers on the right hand side, and we are going to refer to this thing as the right hand side column, or perhaps there's a matrix there. So this is right hand side. It is quite common that we need all of them all at the same time. In some cases we separate them and treat them separately. In some cases it might make sense to apply them all next to each other. In that case I will have a matrix 2 minus 3 minus 1 4 7 1 0 3 minus 3 minus 2 9 0. Sometimes they draw some dotted line here, sometimes they don't. At any rate, you have to keep in back of your mind if you have included the right hand side or not. In case you do, this whole thing is going to be called the augmented matrix. So what we are trying to say is that these are equivalent. If you have that, you can write this. If you have this, you can write that one. Of course, you can choose the name of your variables, whatever you want. That is not so significant. Aside from the name that you're choosing, these two are representing the same fact. So to say to solve an equation is going to be equivalent to certain activity that we are going to perform on this matrix. When you take this equation and do to it what you have learned to do in junior high, we are going to refer to our activities as operations on equations. If we do it to this matrix, we are going to refer to it to what we are doing as operations on rows or columns. So this matrix has a bunch of rows. This is the rows that we have. Now you can start playing with these rows. The play that you are going to do is going to be the kind of stuff that you were doing for solving an equation. So in case that is the word view that you pick, we are going to talk about row operations. Now let's see what are the things that you actually do to solve an equation. Let me maybe keep these things here and erase the stuff that I'm not going to need. Okay. Yeah. So let's take a look at the left hand side, and okay, let me just pick another example to carry out. Here's another system. It's 3y plus 2z is equal to 7, x plus 4y minus 4z is equal to 3, 3x plus 3y plus 8z is equal to 1. Suppose we want to solve this system. Let's do two things simultaneously just to see that these two activities are very similar to each other. So alongside with this one, I am going to also write down the augmented matrix for this thing. We said we want to use the idea of elimination, which we called it the Gaussian elimination. Our objective is to make our equation look like, our objective was to make our equation look like this kind of things, with some entry here, and underneath it, it's going to be all 0. Next, 2 entries perhaps here, and then underneath it will be all zeros, and so on. So we are trying to make a triangular form. Right from the start, we see that there's a little bit of a problem. I want tip of my triangle to be here, so I need some entry in this location. For whatever reason, I insist to say on saying an x here. What can I do? Simply, I can say what? Yeah. What we do, we can just simply exchange these two equations. Simply write this one on the top and second one on the bottom. That is still the same equation, has the same number of solutions. So again, why are we doing this? Just because we want to preserve, to create that kind of a look. I want something on the tip of this triangle here. So I come back down here, so I move this one up. So x plus 4y minus 4z is equal to 3. Move that one down. Now you can move it down here or somewhere else, but it's either way you will get the same answer. So I'll have now 3x plus 3y plus 8z left where it was. So we say these two equations, these two systems are equivalent. What do we mean equivalent? Equivalent means whatever x, y, z solves this, obviously solves that one too, and vice versa. Same thing on the matrix. The activity that we are performing on this matrix, we are going to call it exchange of row 1 with row 2. Later on, we are going to have abbreviations for these things that we are doing, but right now, if you're solving one of these problems, just write next to it, what is it that you did to the matrix. Okay. Again, our objective is to make a triangular form. Triangular form, numbers are up here, and below it are occupied by zeros. So what is it that I don't want to see? I don't want to see this one, or I don't want to see the x here. So on our first line of attack, we try to get rid of all x's in the first column below the very first x. We got lucky by the fact that there wasn't anything here. If there was something there, we would have tried to get rid of it, but luckily it isn't there. All we have to do is to get rid of 3. So now we ask, how do I eliminate this? That's where the terminology comes from. Somehow you want to use this to eliminate that one. Well, what do you do? Yes, very good. So the way we are going to express that, we say we take the first equation, multiply it by -3, or subtract 3 times the very first equation. Very first equation refers to the equation we are looking at in the very last stage, not that guy. So multiply this by -3, add it to the very last equation. That is going to be your new last equation. Or same thing here. Take the very first row, multiply it by -3. So R1 is going to indicate, it's going to be shorthand for the first row. Multiply that by -3, add it to the last row, and the result is going to occupy the last row. Now, here is where the drudgery starts. Doing a lot of arithmetic. You have to do a lot of multiplication, addition, and such. That's the way errors creep in, and you have to watch out, double check before you go down, because these problems tend to have many steps. If it goes wrong here, everything's going to collapse after that, and recovery is not going to be easy. So every one of these stages you go through, you try to double check, so the more time you spend on that, of course, the better it's going to be. On the other hand, you don't want to spend too much time on it because you have to solve the problem. Okay, -3. So first equation is still there. So you notice we are doing a lot of writing. Later on, you probably get the hang of it. You don't need to write as much, but don't try to be economical first round. -3 times that plus this, that creates 0. That's what we want. So it becomes 0. Now it changes everything else. What becomes of this one? -9. Why? Because we say -3 times 4 is -12. Plus 3 makes -9. And then how about this? -3 times that is 12z plus 8. I get a total of 20z. How about the right hand side? Yeah. Whatever you do to the left, you are also doing it to the right. So this becomes -9 plus 1 makes -8. Or if you didn't care about writing the x, y, z's, this is same 1, 4, -4, 3, 0, 3, 2, 7. -3 times that plus this one is 0. -3 times 4 is -12, and this guy is -9. -3 times -4 is 12, and an 8 is 20, and -3 times 3 is -9, and a 1 is -8, which is exactly what we have here. Next, okay, we are marching toward this form. So on the first line of attack, we made these guys into 0. Next round is going to be a shorter column, but there is going to be zeros there too, and so on. We are going to march forward. So let's see. Okay, what combination of these equations is going to destroy the y here? We want to try to get rid of it, and that's where some common mistakes happen. Which two equations should play? Yeah, equation number 2, this current equation number 2 and current equation number 3, these are the ones that we are going to allow them to play. Why? Why can't I use equation number 1 to get rid of this? Yeah, if you, you are going to mess up what you worked so hard to create here. So now equation number 1 is out of the picture. It's not going to play any role for a while. We're just going to use the equations that is not going to mess up the form that we have created. So what should I do? Second row by 3 and add, and that is going to place the third row, or same thing here. Row 2, triple it and add it to row 3, and the result reserve it in row 3. When we say triple row 2, we don't really go ahead and change row 2. That's typically not going to help us. Leave it alone. Just multiply this in your head and add it in your equation. So there we go. X plus 4y minus 4z is equal to 3. 3y plus 2z is equal to 7. Now you help me out here. You double check. 3 times 3 and minus 9 makes you 0. What do I have here? 26. Z is equal to 21 minus 18 is going to become 13. Or 1, 4 minus 4, 3, 0, 3, 2, 7, 0, 0. And here we said 3 times that, and this is 26, better be same number. 21 minus 8. Okay, it looks like we succeeded. Every now and then there's going to be a bit of problems. Things don't line up perfectly the way you expected. We are going to talk about those cases later on. Those are like kind of pathological situations where something not going to be exactly the way you wanted it. But right now we are on track. So now what we have created is going to be called echelon form. Okay, so what we have here is referred to as the echelon form. Because they use that expression in the military, or the way the geese fly or something like that. So we have an echelon formation. And what do we do now? Once we have this format, what did we say we do? Yeah, back substitution. Once you have that format, you do back substitution. You start at the bottom, you go back up. You are essentially still doing Gaussian elimination, but calling it by a different word. So what is my z? I start from the last equation, z. So you clean it up as much as you can, so that makes your life a little bit easier. We step backward. We have 3y plus 2z is equal to 7. So 3y is going to be equal to what? 7 minus 1 is 6. So your y is going to be 2. So far we have 2 of the mystery quantities, and then we go back up. So we have x plus 4y minus 4z. So if we went back to the first equation, substituted, what we got, right hand side is 3. So x plus 8 minus 2 has to be 3. So x is going to be 6 going to the other side, negative 3. We write it in a nice looking column or row. In the order we got them. If you want to check it, best policy is to go back and check very first equation that we had. Let me give also another wording. One of the main sources of error is just copying the problem from the exam paper or the book just to your scratch sheet. That's where the big number of problems happens. Like in a parking lot, most accidents happen in a parking lot. You are not doing anything, just getting going, and you bump it against somebody. So you have to watch out this one. So you double check your entry, and then you double check your steps. You can always, the step that brings you down here, you can take the step back to make sure that you are on the right track. So you take your answers, you check to make sure you are on the right track, and then you will be all set. Now, some of the problems that you are going to be encountering in the homework is going to be just a tad bit tricky. Let me ask you to read the material on the section 1. Some of the items I didn't get to talk about, so just read that section. Do all the problems from 1-1. Do as many of it as it takes for you to be comfortable with all type of question. The very last 4 questions are a little bit trickier, so spend some time on those. So for next time, you want to do at least one example from each type on the range of problems from 1 through 32. You first go according to what is on the blue sheet, and then make sure you have covered at least one of each type. If you have any difficulty with any of them, then try to do 2 or 3. And then you can bring up your questions on Monday. I'll answer as many of them as we can. Good luck and God bless. Anybody has any questions? No, homeworks are not going to be picked up. You're going to ask your questions in class time. I'll go over as many of them as I can. And there might be a recitation section with a student coming and helping everybody. Okay? Huh? Yeah, in a couple of hours they will be out there. Hold on for a moment.